Welcome! In today's session, we'll tackle an intriguing problem titled Add Minimum Number of Rungs. We'll analyze the requirements, explore intuitive and efficient approaches, and break down the solution step by step. Let's dive in. In this problem, you're given a ladder represented by a strictly increasing integer array called rungs. However, there's a restriction: you can only climb to the next rung if the distance between your current position and the next rung is at most dist. If the gap between two positions exceeds dist, you are allowed to add rungs at intermediate positions to make the climb possible. The task is to determine the minimum number of rungs you need to add in order to climb all the way to the top. The input includes the rungs array, which is sorted in strictly increasing order, and the integer dist that represents the maximum climbable distance. The output will be a single integer indicating the number of rungs you need to add to make the climb possible. Each value in this array represents the position of a rung on the ladder, and you start at position 0. Your goal is to climb to the last rung of the ladder. Let's consider the first example where rungs equals 1, 3, 5, 10, and dist equals 2. Initially, you start at position 0. From here, the distance to the first rung, which is at position 1, is within the allowed distance of 2. So, no rungs are needed for this step. Similarly, the distance from 1 to 3 is also 2, which means no rungs are required here either. The same is true for the distance from 3 to 5, which is again within the allowable limit. However, the distance from 5 to 10 is 5, which is greater than dist. To bridge this gap, you need to add two intermediate rungs, one at position 7 and another at position 9. This ensures that the maximum distance between consecutive rungs is no more than 2. In total, you add 2 rungs, so the output is 2. In the second example, the input is rungs equals 3, 6, 8, 10, and dist equals 3. Starting at position 0, the distance to the first rung at position 3 is exactly equal to dist, so no rungs are needed. Next, the distance between 3 and 6 is 3, which is also within the allowable range. Similarly, the distance from 6 to 8 is 2, and from 8 to 10 is also 2. Since all the gaps between consecutive rungs are less than or equal to dist, you don't need to add any new rungs. Therefore, the output is 0. In the third example, the input is rungs equals 5 and dist equals 10. Here, the ladder has only one rung at position 5. Starting at position 0, the distance to the first rung is 5, which is less than dist. Since the gap is within the allowable range, no additional rungs are needed. As a result, the output is 0. The problem comes with some important constraints and edge cases. First, the length of the rungs array can range from 1 to 100,000, and each position in the array is strictly increasing with values up to 1 billion. The maximum distance dist can also be as large as 1 billion. When considering edge cases, if dist is extremely large, you may not need to add any rungs because all gaps will automatically be climbable. If the rungs array contains only one element, you'll need to check the distance from position 0 to that single rung against dist. Additionally, if all the distances between consecutive rungs are less than or equal to dist, no extra rungs are required. On the other hand, if dist is very small, such as 1, you may need to add a significant number of rungs to bridge large gaps in the ladder. These scenarios highlight the importance of efficiently calculating the minimum number of rungs needed to meet the requirements. To tackle the problem, we first consider a brute force approach. The idea here is simple: start from position 0 and check the gap between each consecutive rung in the array. If the gap between two positions is larger than the maximum distance you can climb, which is given as dist, we figure out how many extra rungs are needed to reduce that gap to a manageable size. These additional rungs are placed as close to dist units apart as possible to ensure the gap becomes climbable. While this method is intuitive and straightforward, it requires inspecting each gap in detail and simulating the addition of rungs, which can lead to inefficiencies. The time complexity is n*k, where n is the number of rungs and k represents the average number of rungs added per gap, and the space complexity remains 1. However, this approach becomes impractical for large arrays because of the repetitive calculations involved in simulating the solution for every gap. A more efficient solution employs a greedy strategy. Instead of manually simulating the addition of rungs for each gap, we directly calculate the number of extra rungs required. Let's say the gap between the current position and the next rung is gap equals rungs, current underscore position, where the current underscore position starts at 0. The number of rungs needed to bridge this gap can be calculated using the formula gap1 // dist. This ensures the gap is reduced to a climbable distance while minimizing the number of rungs added. After determining the extra rungs, we update current underscore position to the next rung and proceed until all gaps have been processed. This method avoids repetitive computations, making it highly efficient. Its time complexity is O(n), as we process each gap once, and the space complexity remains O(1). While other strategies like binary search or dynamic programming could be considered, they introduce unnecessary complexity without improving the runtime or clarity compared to this greedy approach. The greedy approach stands out as the optimal solution for this problem for several reasons. First, it processes each gap independently and calculates the exact number of extra rungs needed, ensuring minimal additions. The formula gap1 // dist is both efficient and precise, guaranteeing correctness in every scenario. Additionally, with a time complexity of O(n), this method achieves the best possible performance since each gap must be processed at least once. When we compare greedy to the brute force approach, greedy eliminates redundant calculations, making it significantly faster for larger inputs. Similarly, alternatives like binary search or dynamic programming add unnecessary complexity without yielding better results. In summary, the greedy approach strikes the perfect balance between simplicity, correctness, and performance, making it the most efficient and elegant solution for the problem. To solve this problem, we start by initializing two key variables. The first is current underscore position, which represents the climber's current location on the ladder. Initially, this is set to 0 since the climber starts at ground level. The second is additional underscore rungs, which keeps track of how many extra rungs need to be added to make the ladder climbable. Next, we iterate through the rungs array, where each element indicates the position of a rung on the ladder. For each rung, we calculate the gap between the current underscore position and the rung's position, using the formula gap equals rungs, current underscore position. This gap tells us how far the climber needs to reach to get to the next rung. If the gap is within the climber's maximum reach, denoted by dist, the climber can proceed safely to the next rung. Otherwise, if the gap exceeds dist, we calculate how many additional rungs are required to bridge the gap. This is done using the formula ceil, gap dist /dist. The term gap dist represents the part of the gap that exceeds the climber's reach, and dividing by dist gives the number of intermediate rungs required. The ceiling function ensures we round up to cover the gap completely. These extra rungs are then added to our additional underscore rungs counter, which accumulates the total number of rungs added so far. Once the appropriate number of additional rungs has been determined for a gap, we update the climber's current underscore position to the position of the next rung, whether it was originally in the ladder or added by us. This process continues for every rung in the rungs array. After processing all the rungs, the value in the additional underscore rungs counter is returned as the final result, indicating the total number of additional rungs needed to make the ladder climbable. Now, there are a few key insights to consider. First, the climber's inability to jump beyond their maximum reach, dist, is the core constraint that dictates when additional rungs are necessary. For gaps larger than dist, we use the formula ceil, gap dist /dist, to ensure the gap is fully covered, even if it doesn't divide evenly by dist. Using the ceiling function guarantees that no gap is left unbridgeable. Additionally, the algorithm is highly efficient, as it only requires a single loop through the rungs, resulting in a time complexity of O(n), where n is the number of rungs. This makes it well suited for handling larger inputs. The algorithm relies on a few simple but critical data structures. The rungs array serves as the input, storing the predefined positions of the ladder's rungs. This array is processed sequentially during the iteration. Alongside this, we use two scalar variables, current underscore position, which tracks the climber's progress as they ascend the ladder, and additional underscore rungs, which accumulates the count of extra rungs added. To better understand how this algorithm works in practice, let's go through an example. Suppose the input is rungs equals 4, 10, 18, and dist equals 5. We begin with current underscore position equals 0 and additional underscore rungs equals 0. For the first rung at position 4, the gap is 4, 0 equals 4. Since this is within the climber's reach of 5, no additional rungs are needed, and we simply move to current underscore position equals 4. Next, the gap to the second rung at position 10 is 10, 4 equals 6. This exceeds the climber's reach, so we calculate the number of additional rungs needed using the formula, ceil, open parenthesis 6 minus 5 close parenthesis divided by 5 close parenthesis equals ceil, 1/5 equals 1. One extra rung is added, bringing the total additional underscore rungs to 1, and we move to current underscore position equals 10. Finally, we examine the gap to the third rung at position 18. The gap between positions 10 and 18 is 18, 10 equals 8. Since this also exceeds the climber's maximum reach of 5, we again calculate the extra rungs needed, ceil, open parenthesis 8 minus 5 close parenthesis divided by 5 close parenthesis equals ceil, 3/5 equals 1. Adding one more rung increases the total additional underscore rungs to 2, and we update the current underscore position to 18. After processing all the rungs, the algorithm concludes, and we return additional underscore rungs equals 2 as the final result. This means 2 additional rungs are needed to make the ladder climbable given the specified constraints. By breaking the problem into manageable steps and focusing on the climber's reach, this algorithm efficiently determines the minimum modifications required to ensure a safe ascent. This solution solves the LeetCode problem number 1936, add minimum number of rungs, by iterating through the ladder's rungs and ensuring the climber can reach each rung within the maximum allowed distance, dist. 1. Initialization. We define 2 variables, current underscore position starts at 0, ground level, and additional underscore rungs counts the extra rungs we add. 2. Iterate through rungs. For each rung in the rungs list, we calculate the gap between the current underscore position and the rung's position. If the gap exceeds dist, we compute how many rungs are necessary to bridge the gap. The formula, gap1, // dist determines the number of intermediate rungs needed. 3. Update position. After processing the current rung, we update current underscore position to the rung's position. For output result, at the end of the loop, we return additional underscore rungs, which contains the total number of extra rungs required. The algorithm efficiently handles the problem in O(n) time, where n is the number of rungs, ensuring scalability for large inputs. It also accounts for edge cases, such as when no extra rungs are needed or when gaps vary widely between rungs. This is the Java implementation of the LeetCode problem add minimum number of rungs. The logic mirrors the Python implementation but uses Java's syntax and type system. Key differences include explicit type declarations, the use of Java's primitive types, and the absence of Python-specific constructs like list slicing. The method iterates through the rungs, calculates the gap to the next rung, and determines how many additional rungs are needed to ensure the gap does not exceed the maximum allowable distance. In this problem, we need to figure out the minimum number of rungs to add to a ladder to ensure that the gap between any 2 successive rungs does not exceed a given distance, dist. We begin at position 0, which represents the ground, and work our way up to the topmost rung. For example, consider the ladder with rungs at positions 1, 3, 5, 10, and dist set to 2. Here, our task is to check the gaps between the rungs and add extra rungs wherever the gap exceeds 2. To start, we initialize current underscore position to 0 and additional underscore rungs to 0, as we are at the ground level and have not added any rungs yet. Now, as we iterate through the rungs, we first encounter the rung at position 1. The gap between the current position, 0, and the rung, 1, is 1. Since this gap is less than or equal to dist, no additional rungs are required. We then update current underscore position to 1. Next, we check the rung at position 3. The gap between positions 1 and 3 is 2, which again is within the allowed distance, so no rungs are added. We update current underscore position to 3. Similarly, for the rung at position 5, the gap is 2, which is acceptable, so we move current underscore position to 5. However, when we reach the rung at position 10, the gap from the previous position, 5, is 5, which exceeds dist. To bridge this gap, we calculate the number of rungs needed as 5 to 1 / 2 equals 2, and we add 2 rungs. This brings the total additional rungs to 2, and we update current position to 10. Thus, the minimum additional rungs required for this example is 2. In the next example, we are given rungs at positions 4, 8, 12, 16, and dist is set to 3. Starting with current position at 0 and additional rungs at 0, we begin evaluating the rungs. The first rung is at position 4, and the gap from the ground is 4, which exceeds dist. To address this, we calculate 4 to 1 / 3 equals 1 additional rung, bringing additional rungs to 1. We then move current position to 4. For the second rung at position 8, the gap from position 4 is again 4, requiring another rung. We calculate 4 to 1 / 3 equals 1 and add one more rung, making additional rungs equal to 2. We then update current position to 8. Similarly, the gap to position 12 is 4, so we add another rung using the same calculation, bringing the total to 3, and set current position to 12. Finally, the gap to the last rung at position 16 is also 4, which exceeds dist. Once again, we calculate 4 to 1 / 3 equals 1 additional rung, increasing additional rungs to 4, and update current position to 16. For this example, the total number of additional rungs required is 4. Moving to another example, consider the ladder with rungs at positions 3, 6, 9, 12, 15, and dist set to 5. We initialize current position to 0 and additional rungs to 0. As we iterate through the rungs, the first rung is at position 3, with a gap of 3 from the ground. Since this is within the allowed distance, no rungs are added, and we set current position to 3. Similarly, the gap to the second rung at position 6 is 3, so no additional rungs are needed, and we move to 6. The same reasoning applies to the rungs at positions 9, 12, and 15, as each gap is 3, which is less than or equal to dist. Therefore, no additional rungs are needed throughout this example, and the final output is 0. This demonstrates how the solution dynamically calculates the required rungs based on the given distance and the placement of the ladder rungs. The time complexity of this solution is O(n), where n represents the number of rungs in the input list rungs. This is because the algorithm processes each rung exactly once during the iteration. Specifically, the for loop iterates over the entire rungs list, performing operations for each element, which results in O(n) time. For every rung, the gap to the next rung is calculated using the formula gap equals rung current position. This computation is an O(1) operation. Additionally, if the gap exceeds the allowed distance dist, the number of additional rungs required is determined using integer division, gap1 / dist, which is also an O(1) operation. These constant time operations are executed for every rung, so their total contribution remains O(n). Since there are no other operations outside the loop that scale with the input size, the overall time complexity of the solution is O(n). The space complexity of this solution is O(1), meaning it uses a constant amount of memory regardless of the input size. This is because the algorithm does not rely on any additional data structures or recursion. The input list rungs and the integer dist are provided as arguments, and they do not require additional space allocation during execution. The algorithm uses a few scalar variables, such as current position and additional rungs, which each require only O(1) space. Similarly, temporary variables like gap are also scalars and do not scale with the size of the input. Since no extra space is allocated beyond these variables, the total space usage remains constant at O(1). When comparing approaches, a brute force or naive approach might involve simulating the process of adding rungs one at a time until all gaps between consecutive rungs are less than or equal to dist. This method would repeatedly modify the list and recalculate gaps, leading to a time complexity of O(k), where k is the total number of rungs after all additional rungs are inserted. Since k can become significantly larger than n, this approach becomes inefficient for large inputs. In contrast, the optimal solution avoids modifying the input list entirely. Instead, it directly calculates the number of additional rungs required for each gap using mathematical operations. This approach reduces the complexity to O(n), which is much more efficient and scalable than the naive method. In the best-case scenario, all gaps between consecutive rungs are already less than or equal to dist, so no additional rungs are required. Even in this case, the algorithm still iterates through all n rungs, resulting in O(n) time. On average, some gaps will exceed dist, requiring additional rungs to be calculated. However, since the operations for each rung are constant time, the overall complexity remains O(n). In the worst-case scenario, all gaps are significantly larger than dist, meaning the algorithm must compute the maximum number of extra rungs for each gap. Even so, the number of rungs to process remains fixed, so the time complexity does not change from O(n). Mathematically, the algorithm performs n iterations of the loop, and each iteration involves constant time operations such as subtraction, comparison, and integer division. This results in a total runtime of t(n) equals c*n, where c is a constant. Ignoring constants in big O notation, the time complexity is O(n). Similarly, the space complexity remains O(1), as no additional memory is used beyond the input and a few scalar variables. When solving this problem, there are a few common mistakes to watch out for. First, many solutions fail to account for the initial position, which is 0. This is a critical oversight because the gap between the starting position and the first rung is just as important as the gaps between subsequent rungs. Ignoring this can lead to underestimating the number of steps required. Next, some assume the gaps between rungs are uniform, which simplifies the problem incorrectly. In reality, the gaps are often non-uniform, and making this assumption can lead to incomplete or invalid solutions. Finally, handling edge cases improperly is another frequent mistake. For instance, scenarios with very few rungs or gaps that don't require additional steps can trip up solutions that lack thorough testing for such situations. These edge cases are often emphasized in interviews, so missing them can result in failing key test cases. Another issue to be mindful of is inefficient iteration. Using nested loops or performing redundant calculations to traverse the array of rungs can unnecessarily increase the time complexity to O(n²). This is avoidable because a single pass through the array, or an O(n) solution, is sufficient. Additionally, there's the risk of making off-by-one errors when calculating the required steps. This often happens when rounding up is overlooked or when the indexing of the array is mishandled. Calculating steps accurately requires careful attention, especially since rounding up ensures you account for partial steps that still contribute to the total effort needed. Small errors like this can derail an otherwise correct solution, so precision is critical here. To perform well in interviews, it helps to focus on a few key insights. Recognizing patterns is essential, as many array-based problems, including this one, revolve around identifying relationships between consecutive elements. Developing a general formula or approach to handle varying gaps can streamline your solution. It's also important to analyze edge cases thoroughly. For example, consider empty arrays, minimal input sizes, or extremely large values, and always ask clarifying questions about constraints. Efficiency is another crucial factor. While a brute force approach might work for small inputs, interviewers often expect optimized solutions, such as O(n) complexity. Lastly, if you identify multiple approaches, take the opportunity to explain the trade-offs. Discuss why one method might be better in terms of performance, simplicity, or adaptability to variations of the problem. This problem shares similarities with several other LeetCode challenges. For instance, LeetCode 1346, which involves checking if an element and its double exist, also requires careful array traversal based on specific conditions. Another related problem is LeetCode 410, which focuses on splitting an array into partitions based on gap-based criteria, making it conceptually similar. Similarly, LeetCode 1011 addresses the challenge of finding an optimal way to ship packages within a given number of days, involving binary search to optimize step sizes. Finally, LeetCode 875, which deals with determining how quickly Coco can eat bananas, also uses a binary search approach to calculate the required steps. Practicing these problems can deepen your understanding of array traversal and optimization techniques, which are valuable in tackling variations of this challenge. There are alternative approaches to solving this problem, each with its own trade-offs. A binary search approach can be used to determine the minimum step size required to traverse the gaps. This method reduces the time complexity to log max_gap, but it is more complex to implement and may not be as intuitive. Another option is the greedy approach, where you calculate the required steps for each gap and update the count immediately. While this method is simpler, it may require a clear understanding of how to handle each gap independently. For problems with additional constraints, such as a limit on the number of extra rungs within a range, a sliding window approach might be useful. This adds complexity but provides a way to manage range-based constraints effectively. Each approach has its strengths, so consider the problem's specific requirements when choosing the best method. Great job! To sum up, we identified the minimum rungs needed by analyzing the gaps and optimizing our approach. Remember to focus on edge cases and aim for efficiency in your solutions. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!